If I told you that right now, at this very moment, there's a way to cross the entire galaxy in under a minute, you'd probably say I'm lying, but I'm not. Physics allows it. It's real. It's proven. It's happening in a lab in Switzerland every single day. But here's what nobody tells you in the headline. There's a price attached to that minute. And the price is so enormous, so final, that it might be the cruelest rule the universe has ever written. By the end of this video, you'll understand why the fastest way to explore the cosmos is also the surest way to lose everyone and everything you've ever known. And let's get into it. Here's something most people never think about. Distance isn't fixed. It's not a constant unchanging thing painted onto the universe. Distance depends on how fast you're moving. That sounds insane. We're taught in school that a kilometre is a kilometre. That 27 kilometres is always 27 kilometres, no matter who's measuring it. But Einstein proved that's simply not true, not when you start approaching the speed of light. Here's the core idea. If you travel close to the speed of light, distances shrink, not metaphorically, not as an illusion. They actually shrink from your perspective as the person moving. This isn't science fiction. This isn't a what if. This is measured, tested, confirmed physics happening in a machine on Earth right now. And there's one number that I think about more than almost any other number in physics. It's not a huge number like the size of the observable universe. It's not a tiny number like the mass of an electron. It's a number that connects something enormous, the scale of galaxies, with something we've actually built with human hands. That number comes from CERN. Let's talk about the Large Hadron Collider, the LHC. Most people know it as the place where they smash particles together. But what's actually happening inside that machine is one of the best real-world demonstrations of relativity that exists anywhere on Earth. The LHC is a ring, a physical circular tunnel buried under the border of France and Switzerland, and this ring is 27 kilometres in circumference. That's roughly the size of a small city's outer ring road. If you drove around it in a car, it would take you a good 20-25 minutes. Inside that ring, scientists accelerate protons, tiny subatomic particles, to speeds that are almost incomprehensible. These protons travel at 99.999999, the speed of light. Read that again, not 9. The speed of light. The speed of light 9% of the speed of light speed, that the difference between them and an actual photon is almost meaningless in practical terms. And here's where it gets strange. At that speed, distance shrinks by a factor of 7,000. Let that sink in. Not shrinks a little, not shrinks by 10 or 50. It shrinks by a factor of 7,000, which means that same 27 kilometre ring, the one that would take you 20 minutes to drive around, from the proton's perspective, is only about 4 metres in diameter. 4 metres. That's smaller than most living rooms. A ring built by humans, engineered over decades, spanning 2 countries, and to something moving fast enough, it might as well be the size of a hula hoop. This isn't a rounding error or a quirk of measurement. This is a fundamental feature of how the universe works. Space itself compresses when you move fast enough. The faster you go, the smaller the universe becomes from your point of view. And once you understand that this is real, not theoretical, not speculative, but measured in a machine we built, your mind starts asking the obvious next question. If a tiny proton can experience a 27 kilometre ring as just 4 metres, what would a spacecraft experience if it could travel at that same speed? According to the laws of physics, and this is the part that should genuinely blow your mind, if you could build a spacecraft that travels close to the speed of light, you could shrink the distance to other galaxies, not just other stars, not just other planets in our solar system. Other galaxies. Let's use the example most physicists reach for, the Andromeda galaxy. Andromeda is our closest large galactic neighbour, sitting about 2.5 million light years away from Earth. To put that in perspective, light itself, moving at the fastest speed anything can move in this universe, takes 2.5 million years just to cross that distance. That's longer than modern humans have existed as a species. And yet, if you were on a spacecraft moving close enough to light speed with distance shrinking by a large enough factor, you could, in principle, cross that gap in about 1 minute. According to physics, not a loophole, not a cheat code, not fiction. This is what relativity actually predicts, and what the LHC actually demonstrates on a small scale every single day. So in theory, the galaxy, and galaxies far beyond our own, aren't actually unreachable. They're not permanently locked away by distance. If we ever solve the engineering problem of reaching those speeds, the distance problem practically disappears. And it's not just Andromeda. Think about it on a smaller scale first. Alpha Centauri, our closest star system, is about 4.3 light years away. At normal chemical rocket speeds, the kind we currently use, a trip there would take tens of thousands of years. But at speeds close enough to light, with distance shrinking dramatically the way it does for those LHC protons, that same trip could feel like it takes days or even hours to the people on board. Push that same logic further, all the way up to galactic scales. And the numbers stop mattering the way we think they should. A trip that should take millions of years by the light speed limited math we're used to could feel like a short flight to the person actually making the journey. Not because they're cheating the speed limit, the speed of light is still the speed of light, but because space itself is compressing around them as they move, which sounds like the best news humanity could ever receive, except for one detail. One brutal, unavoidable detail that changes everything. Here's the part that flips this entire story from thrilling to tragic. If you travelled to Andromeda at that speed and then turned your spacecraft around to come back to Earth, to tell everyone what you found, to share what you saw, to bring back the discovery of a lifetime, at least 4 million years would have passed on Earth.
4 million years, not 400 years, not 4,000.
4 million, to put that into perspective, 4 million years ago, our ancestors weren't even fully human yet. We're talking about a time scale that predates Homo sapiens entirely. Early hominins were still figuring out how to walk upright and use basic tools when that clock would have started ticking. By the time you got back, everyone you knew would be gone. Not just dead, forgotten, along with everyone who remembered them, and everyone who remembered those people. Human civilization as we currently understand it might not even exist in a recognizable form. Languages, nations, technology, culture, all of it would have been rewritten dozens of times over across 4 million years. This is the trade-off baked into the very structure of the universe. Speed through space always costs you time. Not metaphorical time, literal, measurable, unforgiving time. The faster you move relative to something else, the more that something else ages compared to you. This isn't punishment, it's not a glitch. It's how space-time itself is built. Einstein didn't invent this rule, he discovered it. It was already there, woven into reality, waiting for us to notice it. So here's the paradox we're left with. We technically could explore the galaxy and beyond. The physics doesn't forbid it, but coming home to actually tell anyone what you found, that's forbidden. Not by engineering limits, not by fuel constraints, not by any problem we could someday solve with better technology. It's forbidden by the structure of the universe itself. Now, you might be thinking, okay, this sounds cool, but is this actually real, or is this just a fun thought experiment physicists use to sound smart? It's real, and we have proof right here on Earth that doesn't even require spaceships. Cosmic rays constantly strike Earth's upper atmosphere, creating particles called muons. Muons are unstable, they decay extremely fast, so fast that by classical physics most of them should never survive the trip down to Earth's surface. They should decay in the upper atmosphere and never reach the ground. But they do reach the ground in huge numbers, detected constantly in labs all over the world. Why? Because those muons are moving at extreme speeds, close to the speed of light. And at those speeds, time dilates for them. From our perspective on the ground, their internal clock runs slower, giving them just enough extra time to survive the journey down. This is the same effect, just at a smaller, more survivable scale. It's the same rule that would apply to a spacecraft heading to Andromeda. We're not describing a hypothetical law. We're describing something happening above your head right now that we've measured with precision instruments for decades. There's another everyday example, and this one might surprise you: GPS satellites. The satellites orbiting Earth that your phone uses for location are moving fast enough and are far enough from Earth's gravity that relativity actually affects their onboard clocks. Engineers have to correct for this time difference every single day, otherwise your GPS location would drift off by kilometers within hours. So this isn't abstract math confined to chalkboards and physics papers. This is a rule embedded so deeply into reality that we have to account for it just to make your phone tell you the right street to turn onto. At this point you might be wondering, if the physics allows it, why haven't we built a spacecraft like this already? The honest answer is energy. an enormous, almost absurd amount of energy. As an object with mass gets closer and closer to the speed of light, the energy required to accelerate it further increases dramatically, not in a straight line, but in a curve that shoots upward the closer you get. To actually reach the speeds we're talking about, for something the size of a spacecraft carrying human beings, would require energy on a scale we simply don't have access to yet, using any technology we currently understand. The LHC can do this with individual protons, tiny particles, almost no mass at all, using an entire underground facility built by thousands of scientists across dozens of countries. Scaling that up to a spacecraft with mass, life support and passengers isn't just harder, it's a difference of magnitude that current physics and engineering haven't found a realistic path around. So this isn't science fiction pretending to be real, it's real physics confirmed and measured that we simply don't yet have the engineering capability to use at human scale. The rule is proven. The application is, for now, still just outside our reach. This raises something worth sitting with for a moment. If any civilization anywhere in the universe ever solved the engineering problem, if they built something capable of reaching close to light speed, they'd face this exact same trade-off. Explore, but never truly return. Discover, but never truly share it with the world you left behind. Some scientists have wondered if this is part of the answer to the Fermi paradox, the strange silence of the universe, despite how many stars and planets exist out there. Maybe distant civilizations have explored. Maybe they've sent ships, probes, expeditions to other star systems and galaxies. But if they did, and if they came back at all, they'd return to a home that no longer exists in any recognizable form. The civilization that sent them might be long extinct. The knowledge might never make it back to anyone who could use it. It reframes exploration entirely. On Earth, exploration has always meant going somewhere and coming back to tell the story. That's the entire structure of history, from ancient sailors to modern astronauts. But relativity tells us that past a certain speed, coming back to tell the story stops being the reward. It becomes, in a very real sense, impossible in any meaningful human sense. You could see the wonders of the universe. You could witness things no human eye has ever seen. But the story dies with you on a planet that no longer remembers who you were. That's not a technological limitation we can engineer our way out of with better fuel or better computers. It's not solvable in the way we solve normal problems. It's a fundamental cost, written into the fabric of space-time itself, the moment you decide to move fast enough to make the journey worthwhile. There's an interesting flip side to consider too. What if the goal was never to come back at all? Some scientists and science fiction writers have proposed the idea of generation ships, vessels where the travellers never intend to return, where their descendants, born and raised on the ship, are the ones who eventually arrive somewhere new. For those travellers, the passage of Earth time wouldn't be a tragedy to avoid, it would simply be irrelevant, because the mission was never about coming home, it was about becoming a permanent, one-way branch of humanity, planted somewhere else entirely. That reframes the whole idea one more time. Maybe the question isn't how do we explore and still make it home. Maybe if we ever do this for real, the question becomes, are we willing to let go of home completely in exchange for seeing what's out there? That's not just a physics question anymore, that's a deeply human one. So here's where that leaves us. We could, in principle, explore the galaxy and galaxies beyond our own. The physics genuinely allows it. Distance is not the wall we always assumed it to be, but the moment you're fast enough to make that journey short, you've also made your return meaningless. Getting to actually chat to everybody about what you found, sharing the discovery, being celebrated for it, having anyone alive who even remembers asking the question in the first place, that's forbidden. Not by rockets, not by fuel, not by budget, by the structure of the universe, by the way relativity works. It's one of the strangest, most humbling truths in all of physics. The universe doesn't stop us from exploring it. It just makes sure that if we go far enough, fast enough, we can never truly come home. If this made your brain hurt a little, good. That means it's working. Let me know in the comments if you had the chance to make that trip, knowing you could never return to the world you left behind. Would you go? Subscribe if you want more of these mind-bending truths about the universe we live in. I'll see